look right at it. Physics time, inertia. We're going to talk about inertia. So write down inertia. And the first thing we're going to talk about is Newton's first law. So remind me, what is Newton's first law of motion? Say it. What's Newton's first law of motion? Okay, so we got an object so far. An object.
Newton's first law.
An object.
Stays in motion.
An object that is in motion stays in motion
Until it must act on that.
Let's before we say that bit, which is true, let's also say the other thing. An object in motion stays in motion, and
At rest.
an object at rest stays at rest unless what?
Acted on by force.
Unless acted on by, let's be specific about our force.
Outside.
Yeah, we can say outside, that's what it is, but how does the force have to be to make it change its motion? If, look, I'm putting a force on this, okay, I did it a little bit, but now I'm putting a force on this and it's not moving. What does the force have to be to make it move?
Stronger.
What?
Balance.
Unbalanced. Not acted upon by an unbalanced force. Because the reason that I was forcing that little table and it wasn't moving, the reason I'm pushing this little table and it's not moving is because the force of friction is balancing it. So that doesn't make the object change its motion, right? It has to be an unbalanced force to make its motion change. So in this case, this object was at rest, and so it stays at rest until I push on it with an unbalanced force. If it was in motion, which it isn't, but if it was in motion, how specifically would its motion be until acted upon by an unbalanced force? Oh, sorry, I didn't even finish my sentence. Force. What is this motion going to be like, specifically? Will it be doing spirals? It has to be a straight line, right? And what does its speed have to be? Can it change speed? No, but that's a kind of acceleration. So how do we have to describe its speed? Constant, right? So this motion here specifically has to be a straight line at a constant speed. Basically, both of these things are saying the object is not doing what? What is the object not doing in both of these cases? Accelerating. Both of these, there's no acceleration. And we already know that unbalanced forces cause acceleration. And so in both of these cases, there's no unbalanced force, and so there's no acceleration. And this whole thing is called inertia. Inertia, you know the 7 deadly sins. Do you know the 7 deadly sins? Have you ever heard of such a thing as the 7 deadly sins?
Yeah.
Yeah. What are some of them? You know them all? You know any of them?
Coveting your neighbor.
I think you might be thinking of the 10
I
Commandments.
don't know.
Covetousness is kind of one of them. It's envy. Envy is one of the 7 deadly sins.
Oh, is it greed one of them?
Greed, yeah.
Greed.
What'd you say? Lust is one. What was yours?
I said violence.
Wrath is one. We got 4 now. The reason we're talking about this is not catechism, but the reason we're talking about this is that one of them, sloth, which is laziness, that's a sin. The Latin word for sin, or the Latin word for laziness is inertia. If you look at a Latin list of the 7 deadly sins, which, I mean, those two things kind of go together, right? There's a lot of Latin in the Christian church, but the Latin word for laziness is inertia. And the reason I bring that up is because basically these objects don't want, right? They can't think, but these objects want to keep doing what they're doing. Another example I always give with this is that there's such a thing in psychology or in medicine as sleep inertia, which is that when you're awake, you, to some extent, want to stay awake, right? It's like getting on 2 o'clock in the morning, you're like, yeah, I'm having a good time, let's keep partying or whatever, right? Whereas when you're asleep, and you know this one better probably, when you're asleep, what do you want to keep doing? Maybe for the rest of your life, right? You just want to lay in bed and you say, 5 more minutes, Mom, but what you mean is, this is a sad thing. Sometimes I wake up and I literally think, can't wait till I go to bed.
Yeah.
And that's sad, but that's a type of inertia, right? Sleep inertia. I want to keep doing what I'm already doing. Inertia. Does this make sense? Do you have questions about this? There is exactly one thing on which the inertia of an object depends. You know what it is? Inertia depends on what has more inertia, me or this marker. Yeah. Which one's harder to move? Which one's harder to move, me or the marker? Me. I'm harder to move. So what's the difference between us? Well, it can't be that I'm wearing a lavender shirt and the marker isn't, right? That's not the property on which this depends. It's not that I taste salty and the marker tastes plastic. It's not the taste. What is it? Mass. Yeah. Inertia depends on only mass. And we have to be careful. It's not weight, and we'll talk about in a second why weight and mass are different. But inertia depends on only mass. And this means that even in outer space, even if you were weightless, right? Even if there was no weight, there's no force. There is a force of gravity, but in the case of outer space, you're in free fall, so the force of gravity is not an unbalanced force on you. Anyway, even in space, it would be more difficult to move me. Imagine we're all in spacesuits, me and you and this marker. It would be harder to move me out of your way, even floating in space, than to move the marker out of the way because I have more mass. This is inertial mass, right? So inertia depends only on mass, and we can say that how are these two things related? What kind of proportional are mass and inertia? Well, if something has more mass, does it have more or less inertia?
More.
More inertia. Something that has more mass has more inertia. So if mass goes up, inertia goes up. If mass goes down, inertia goes down. So they are what kind of proportional?
The same as directly.
Directly proportional, yeah.
Oh.
Hand in hand, Jada is saying pretty much all the time when this comes up, but it is technically known as directly proportional. When one thing goes up, the other also goes up. So one way that we measure, let's do a stricter definition of mass here real quick. I'm just going to kind of block things that mass is, we've talked about this before, what kind of things, what things in the universe have mass? All what has mass? What's the universe made out of? Yeah, all matter has mass, right? The universe is made out of only matter and energy, and of those two, matter has mass. Matter has mass. So we could say that mass is a measure of how much matter is in an object. That's all mass is. Remember, we define inertia a little bit as how hard it is to change the motion of an object. Mass is a measure of how much matter is in an object. Do big objects always have more mass? Think about my aired up globe in the back. Does that have more mass than this book? Probably not. So do big objects always have more mass? So mass is not, let's write this down, mass is not volume, right? Bigger objects don't always have a higher mass. As a side note, what is the property we call how much mass something has per unit of its volume? Do you remember? You're represented with the Greek letter rho.
Oh, golly. Density.
Density, yeah. So mass density and volume are related, right? So for a given object, for two objects with a given density, if they have the same density, the bigger one will also have the bigger mass. But mass is not always volume, right? A bigger object does not always have a larger mass. Mass is also, and we talked about this 1 second ago, and I told you we'd come back to it, and here we are. Mass is also not, mass is not weight. This one's a little bit more confusing because here on Earth, the way that we measure mass is by measuring weight. Even when we go to the lab and we use our scale to measure the mass of something, we're really measuring weight. But mass is not the same as weight. Mass, remember, is a measure of how much matter an object has, whereas weight is what? How much what is happening? How much gravity is pulling on it. Weight is, oh goodness, let's spell it right. Weight is the force of gravity acting on an object. So how come it's okay here on Earth's surface and only on Earth's surface? How come it's okay for us to use weight as mass? How come we can measure weight in grams with our scale?
Because our gravity is consistent.
Yeah,
So
because
that's
it's
basically the same thing.
exactly right. So we have the same force of gravity, the same acceleration of gravity acting on all of us. So here on Earth's surface, we can use weight as a proxy for mass. That means we can use it in place of using mass.
It'd be different if we were on a different planet.
Exactly. If we went to, say, the moon, would our weights be the same? No. But would our masses be the same? Yeah, because we still have the same amount of matter. We just have a different force of gravity acting on us. And you remember talking about balanced and unbalanced forces, right? Real quick before we end the video, let's talk about what net force is. Net force is what we call the total amount of force acting on an object. This says net force is the total amount of force acting on an object. So, give me an object. Give me an example of an object that you think I can draw.
Watermelon.
Did you say origami?
Watermelon.
Watermelon. That'll be easier than origami. Thank you for not saying origami. So if I have a watermelon, watermelons are usually red, right? No, whatever. Here's a red watermelon.
Tomato.
Yeah, I don't have green. I don't have green.
It's a tomato now.
Okay, it's a wavy tomato. So here I have my wavy tomato. If there's a force acting on it, right, we'll say gravity. The force of gravity is acting on it to a strength of force of gravity equals, I don't know, we'll say 240 newtons. It's a pretty heavy watermelon. 240 newtons of gravity is acting on it. Right now, are the forces balanced or unbalanced?
Balanced.
Try again.
Unbalanced.
Unbalanced. There's only one force acting on it. We could say that at this point, the net force is just down, right? So what's this object doing? Falling, right? Specifically, it's falling here. If we set it on a table instead, and now there's another force acting on it. Do you remember what we called this force? The force that holds it up from a surface? This is called the normal force, F sub n, which is, and we're going to write this down, the normal force. And in this case, it also equals 240 newtons. So now, what do these two forces add up to? The net force, as we add them together, equals what? Because they're in opposite directions, so 0. The net force is 0. So are the forces balanced or unbalanced? Balanced. So now is its motion changing? No. So we add up these forces together to get the net force. What about in this case? What if, I don't know, I'm skydiving. Here's me skydiving, you know, like I do. Gotta put glasses on it. And I catch up to this watermelon, and now the force of gravity is still pushing it or pulling it down 240 newtons. But I come up and I rudely push it down with another 200 newtons. Right? If I push it down, what's its net force now? 440. Now the net force is 440 newtons down, right? Because the forces are in the same direction. So if they're opposite, we subtract them. If they're the same, we add them. What happens if they're at an angle? We can do our favorite thing. Math. We can do specifically what? Let's just write this down. If the forces acting on an object are at an angle, use, I'm going to erase this little box here, use what kind of math? Yeah, trigonometry, but we call the process specifically what? Starts with a V.
Some old hippie.
Yeah, we have SOHCAHTOA, but we then at an angle, we use vector what?
Vector math.
Vector math. I call it vector addition. And I like for you to do it trigonometrically. Maybe we'll do a few of those on video. But basically, what I told you last chapter about vector addition, it doesn't go away, right? We did it for velocity in the last chapter. We're going to do it for forces in this chapter. Bye.